Hi, good morning, everyone. Thank you for coming. Hope all of you are okay. These are a bit of some crazy times that we've been through. And first, it's important that all of you know that we are aware of the challenges that these times bring us, and you've all hopefully received messages about some modifications to the schedule that that we decided to do. If anyone has any specific problem, miluim, whatever, so please talk to us, let us know about it. Okay, so today we'll be talking about generative models. And before we start, I just want to thank my co-authors, all the guys helped me preparing these slides. And I'm not going to name all of them because I'm actually kidding. These are all generated faces. They don't exist. And I also want to say that some of you that have been to the Introduction to Computer Vision course probably heard some parts of this lecture, but not all of it. Okay, so it's not exactly the same. And also that today is going to be sort of the first part. So today we'll be talking about Generative Adversarial Networks, GANs, and we're going to have a tutorial with Niv that is going to be not this week, it's going to be next week about non-adversarial generative models. So, okay, so here's our agenda for today. And what we're going to cover, so we're going to start with the motivation and what are generative models. And then we're going to do this introduction to GANs, and we're going to understand what exactly the challenge is there and what we're trying to do and how you evaluate it and how it works. Then we'll be discussing this word called image-to-image translation or conditional GANs. We'll talk about ways to improve GANs, and then we'll talk about some more advanced stuff about GANs. And then in the tutorial next week, you'll learn about variational autoencoders and quantized variational autoencoders and IMLE. These are non-adversarial models. So let's start with the goal and the motivation. So the most basic goal of generative models is a very simple thing, actually. So you have this data, you have this distribution of data, but you have some instances of it. And what you actually want to do is to somehow be able to generate new data, such instances that match this distribution that you have, but novel ones. And this sounds kind of a modest thing to do, but this goes very far to very impressive things like the faces you've seen before. So it can be images, text, audio, video, whatever you want it to be. There are many such possibilities of the applications for generative models. And when you're trying to think about reasons for why generative models exist, why one would want them, so there are some very obvious reasons. So first of all, it's really cool to be able to generate images, and you may use generative models to create more training data for supervised learning, and you can do very cool stuff for computer graphics and, for example, to create anonymous figures and by this keep privacy and create textures and structures for computer games. You can do all this image-to-image stuff that we'll see that can be sometimes very useful. And there are many applications. Some of them you've maybe seen. You have this avatar of yours, or this about a year ago, everybody was talking about this face app, and where you can see how you look when you're older, and simulations. And all of these are really cool and nice, but I hope that by the time we're done today, I'll be able to convince you that generative models are actually more than this, because generative models is an approach, and it's the correct approach for any situation when you have more than one valid solution. Okay, so we'll see it as we go on, but the basic thing is that a generative model describes distribution, and in most of the problems that we're trying to solve in AI in general, usually the correct solution is some kind of distribution. It's distribution of possible solutions. So you can basically divide generative methods to three approaches. So the first one would be parametric distribution estimation. We'll see an example for this in a second, but this basically means, okay, we have data, let's try to estimate its distribution, and then we can do whatever we want with it. The second one is called autoregressive models, and you're actually already familiar with this one because you've done this last week or the week before. You've done it with the Shy. This is the all those text models you've seen, everything, or the transformers. You can, I don't think you've seen causal CNN, but it's basically very similar in the general approach. And these are all sequences. So autoregressive models, they generate stuff one by one. And lastly, what we're going to be talking today, and actually also in the tutorial, and what we're going to spend all our time of generative models about, is a thing called latent space mapping. And we'll explain what this is just in a few minutes. Okay, but this is what we're going to do. Okay, I'm going to very briefly talk about the first approach, doing this density estimation. And so the way this works is, let's say I have instances of data. So what I can do is somehow do this estimation, saying some parametric distribution. So in this case, it looks like a Gaussian. So it's very easy to do a Gaussian fitting to data, right? There are only two moments. You just have to calculate covariance matrix and the expectation vector, and then you can match it, and then you can sample from this Gaussian new instances. And so you have the training examples, and then you can generate new examples. Of course, doing this by Gaussian estimation will probably not get you to be able to generate images. This is because the manifold of natural images, or any type of images, is typically not just a simple Gaussian. It's something much more complicated than this. Here is a quick example for generative models that actually can work for simple data that is based on parametric estimation. And the model is called GMM. For those of you who are not aware, it's a Gaussian mixture model. And Gaussian mixture model is exactly what it sounds like. I hope most of you have heard about it before. And let's say I have this data, okay, and this is how the instances look like. This is two-dimensional data. So the first step is that I get this set of samples, and then what I'm going to do is assume that the distribution that this data was sampled from is what we call a Gaussian mixture model, a GMM. And the GMM is just this weighted sum of Gaussians. And then I need to do this estimation, or this fitting, saying what the parameters are. So GMM models typically has let's say k Gaussians, and each Gaussian has one scalar, one vector, and one matrix, the covariance matrix. So we need to estimate all of these. And I guess some of you know the method. If you don't, you can read about it or ask me after class. It's actually really simple and cool. There is this expectation maximization procedure, and then you can find the parameters that maximize the likelihood. Likelihood, also, I believe most of you are aware, is the probability. Is when you have a model that predicts probability, and then you use it to predict the probability of the data that you already have. So that it's like the probability of reality according to your suggested model. This is what we refer to as likelihood, and you usually take the log likelihood. And once you have this, you have a distribution now that maps the entire space you're working in. And the last step is simply to sample new instances out of this estimated probability density function that you now have. So the key here was the parametric thing. We assumed that we know the type of the probability that we have, and we only had to estimate the parameters. So this brings us. So we've been through the motivation and the basic method, and from now on we'll be discussing this latent space mapping, and this will bring us to talk about GANs. So, what is latent space mapping? This is the third out of these approaches that we've just seen. So, let's say I want to be able to sample new instances, novel instances of some distributions of data that I have. So one thing that I can do is use this transformation saying, okay, I don't know what to do with this very complicated manifold, this very complicated probability density function. Usually, you know, for images, this could be millions of dimensions. So what I can do is have this controlled probability density function, say just a simple Gaussian, like a multivariate Gaussian with, I don't know, 256 dimensions and the diagonal covariance matrix, and with the mean equals 0. So, and then what I can do is to learn this transformation that takes me, each time it takes value that was sampled from this controlled distribution and transform it to some value in the in this complicated manifold. And perhaps this is a more easy setup where I can learn how to do such a transformation. And this is based on this whole probability thing. So that you want to maximize the likelihood of the data that you have. So you can call this P of X. And if you have something that is parameterized, and we're in a deep learning course, so you can probably guess by now that in most cases this theta you see here is weights of a neural network. So you have this whole probability thing. So P of Z, this would be the distribution that you get to decide. So this for example can be just this simple normal distribution, and then you have this. So this is this one, and then you transform it using this model that takes you from Z to X, and this has some probability for each X given some Z. And if you take this full integral, what you get here is this probability or probability density function over like a general one that you want it to be maximized for the instances that you have. The thing is that usually when taking this approach, you're not going to be able to say anything smart about P. So you don't know what this distribution is in general. You can say what the distribution is for some instance, And the reason is that this theta here, this mapping thing that you have is going to be very complicated. So it is parametric, just like GMM, just it has millions of parameters and it's very hard to handle. But what you can do is sample new examples. So to sample, all you have to do is sample some instance here and then transform it here, and then you get some, say, image or whatever it is that the type of data that you're now trying to generate. Okay, so you're able to generate new data, but you're not very able to say like something smart about the distribution itself. Okay, so now that we understand this, so next thing would be trying to find some method to make this thing sort of work, right? So I'm going to make a suggestion, and then I want you to tell me what you think about my suggestion. So this is what I'm suggesting now. So I'm going to have this random pseudo-random generator, and I'm going to just sample this a random vector out of a normal distribution, call it Z. On the other hand, I have this data set, say, of images, and now just by random, I'm going to just sample one image out of this data set. And I'm going to say that this noise here that I just sampled, this is the input, and this image that I took from the data set, it's going to be the label. And now I'm going to train a neural network, and I'm going to train it such that the loss is going to be MSE loss just between the output of the network and this label I have, the image that I just sent. So that each time I have one noise, one image, and I train the neural network to do exactly what we said before, and this is to map noise to image. So what do you think about my idea? Is it going to work? So Raphael doesn't like it. Can anyone share some thoughts? Why wouldn't it work?
You hear me?
Yeah.
Well, I think this will fail because of the randomness on both sides. So the network will have to learn a very random mapping from a random noise to random image. And when you sample another thing, you can get the same image for different noise. And this will be a problem to learn,
so,
I guess.
So, okay, great. So what Raphael is suggesting is some kind of problem with the arrangement of the latent space that we're going to experience, and I agree. And it's more than it's actually a bit more than that, but this is exactly the direction. So let's say I have this. I'm sampling from out of this Gaussian, and here is this supposedly complicated manifold. So I take this one noise, and it is mapped to some instance here, and then I sample again, and this is a noise very close or even the same, and I get something that is totally different. And another thing that can do is that I have a very different noise. I'm going to get about the same result here, and this doesn't look right at this point. Because something is going to be, this is exactly what Raphael mentioned. So something about the latent space is going to be very not natural. It has to be a continuous function. But we actually need to take one more step. This feels bad, but we're not seeing why it's very bad yet. So here's another thought. Let's think about the expectation. Okay, so when we train a neural network, what's going behind the scenes is that we're trying, we're doing stochastic gradient descent, so we're trying to get to the expectation. So what's going to happen in the expectation? Say we infinitely train this, okay? So what's going to happen is that if we had infinitely many epochs, so each possible noise will eventually meet every possible instance from the images infinitely many times. And if we're using MSE, then there is and for a specific noise, for every type of noise, the best solution will be going to this mean. Okay, going to the mean of all the possibilities. Okay, think about it. And eventually, what I'm saying to you is that you have some possibilities, and I want you to guess something. I want you to guess this pixel values, but what I want it to be is as close as possible to all the images that you've seen with some metrics. Say, so here we have the least squares matrix. Okay, the L2. So for the L2 solution, you're going to get the mean of all possible images. It will probably be this grayish image. And if you use a different metric, so if you use L1 Manhattan distance, then you're going to get the median, and whatever you do, you're going to get some kind of centroid. And this is the basic fact about what we call discriminative models. So these are models that converge to this centroid. So this is a problem. This can't be a generative model, and this can't work. And this is the reason generative models have to be different in essence from discriminative models. So are we good up to this point? Okay, great. If you have any questions, please do ask. So, we need to make ourselves familiar with generative adversarial networks. And at the time, so you're going to learn about VAEs in the tutorial next week. But the spoiler is that the basic VAE was mathematically impressive, but its results were not impressive comparing to what GANs were able to do. And the year 2014, Ian Goodfellow came up with the GANs, and since then, the number of GAN papers was getting very high, incredibly high, and it's one of the most important inventions of, let's say, the last decade. And this is the guy, Ian Goodfellow, when he first joined Google, today in Apple, and invented this in Yoshua Bengio's lab in 2014. And so this is one of the really core ideas, one of the most important developments of deep learning in general. So let's try to intuitively build our understanding of GANs and what they're actually doing. And for this, I'll ask you these questions. So, and the question is, what makes a good counterfeiter? Okay, say I want to create fake money, or you know someone who makes fake money. I hope you don't. So how can you judge him? In what way you can say if he's doing a good job or not? Any ideas?
You can judge him by how consistently he fools the guy who checks the money.
Okay, so I'm getting the feeling that Rafael has been to my talk in the intro class, and okay, so, and this is actually the idea. So a good counterfeiter is one that can fool a good cop. Okay, because if he can fool me, I know nothing about identifying fake money. So if he can fool me, this doesn't impress anyone. Okay, that is not doing a very great job. But the better the cop, I think it's cops that need to be able to check whether money bills are real or not. So if you can fool a good cop, a cop that is good at his job, and the better the cop is at his job, and this thief was able to fool him, then it means the better the thief is in doing his job in creating this fake money. And this is sort of the intuition that we want to have when discussing GANs. Okay, and we're going to name these this counterfeiter and this cup. So this counterfeiter is called generator, and this cup is called the discriminator. And naturally, from the from the topic that we're learning in general, so you can probably guess that both of them are going to be neural networks. So we're going to have these two neural networks competing each other, called the generator and the discriminator. And we're going to train them exactly for this thing, this philosophy, saying what we care about is this generator. This is what's going to generate for us these novel instances of data. And we're going to go with this intuition that a good generator is one that can fool a good discriminator. We want both of them to be strong. Okay, so the motivation here is clear. Are we okay? Great. So let's see how we approach this thing, how we train it. So let's first talk about how we train the discriminator. Okay. So naturally, I'm going to have this data set. This is the data that I want to create new instances of. And I'm going to sample a batch of instances, and I'm going to feed it to the discriminator. And now I'm training the discriminator, and the discriminator is a binary classifier. Okay, so what it has to do is to say whether this image is real or fake. So when I train the discriminator, what label do I want to provide for an image taken from the data set?
Real.
Sorry, I didn't get it.
Real or fake?
It's real.
So I want to say real, and when using like a cross entropy loss, I'm going to use the label 1. Okay, so the discriminator provides this. We're using cross entropy. It provides this probability between 0 and 1, with 1 being real. And when I train the discriminator, I'm going to provide a label of 1. And this translates, if you think about the cross entropy, that for this real instance called X, we mark the real instances with X. I want to maximize the log probability. Okay, this is exactly what's happening here. I'm maximizing the log probability of true examples. Okay, I do this back propagation, I update the weights, and I make the discriminator a little bit better on trying to maximize the log probability of real instances. But as a binary classifier, I also need negative examples, these fake examples, right? So how can I come up with a fake example? Anyone have an idea? What would you bring as a negative example for the discriminator?
The output of the generator.
So right. So the output of the generator. So sometimes people say, whatever, you can use noise, just use noise. It's not an image, and this is a fake example. And this is a fake example, but this is a low quality fake example, because eventually you'll be able to say that everything that is not noise is real or something like this. Okay. So the way we generally get fake examples is using the generator. So we take a random noise, we input it to the generator. The generator generates some image that can be good or not good. We'll discuss this in a minute. And this is our fake example. So what kind of label do I want now for the discriminator? So some of you are marking 0, and this is correct. So the discriminator checks it out. And what I want to train it with is the label 0. And this, in terms of cross entropy loss, means that I'm now saying, okay, so for the real example, d of x, I wanted to maximize the log probability. But now what I have is, I don't have d of x, I have d, the discriminator, of g, the generator of z, the random noise, right? So g of z is a fake example, and I want to have, and I want it to be as close, as low as possible, right? So you can see that that, for example, if d of g of z I want to be sorry, I'm maximizing this whole thing, right? I want d of g of z to be as close as possible to 0. And indeed, if this is 0, I get 1 minus 0. Log of 1 is 0, which is the highest I can get from this expression over here. You can check that for every other option that I get. If I have like half, then I have log of half, which is a negative number, and I get lower than 0. So for the discriminator, what I'm trying to maximize is this expression here, log of d of x plus log of 1 minus d of g of z. Okay? And this is the objective for the discriminator. Are we all clear up to that point? Are we okay? Great. Okay. So now we have to just be careful about one thing. So when I generate fake example and I train the discriminator using backpropagation and update the weights, I have to be extremely careful not to backpropagate through the generator, or at least, I mean, you shouldn't backpropagate to the generator, but the more dangerous thing is if you update the generator weights. Okay, we are only training the discriminator, and you know, in practical terms, there is no difference from having two networks or one network. So you have node by node by node, and everything is connected. So you have to be careful here not to update the generator weights according to the discriminator laws. So these are locked, and actually you don't even have, you can like stop the backpropagation just in this point and not calculate the gradients all along the generator as well. Okay, so this is how D is training. Now we have to train G. Okay, we have to train the generator. So to train the generator, I'm going to produce this random noise again. Okay, sorry, let's say the objective first. So let's go back to our philosophy. So the objective for the discriminator is to maximize its ability. This is just a binary classifier, and they want to maximize its ability to distinguish between fake and real examples. And remember our philosophy. We want to be able to fool in the best possible way we can to fool the best cup. So what we're looking for is to minimize. G is looking to have the minimum of the maximum the discriminator is able to do, where the parameters that G controls inside this expression here is just this weights of G over there. So I have this minimax game. So I'm looking for making the best cup do the worst mistake. Okay, and for this I need both the cup to get as best as possible. I'm training the discriminator to be the best binary classifier possible, but I'm also training the generator G to create such example. You see it only it's only expressed here, this G of Z, to create such example that even if D is very good at its job, I'm trying to create examples that will try to fool it. Okay, and this is the minimax game that we have here. So in practice, how do I train G? So I create this random noise and I generate an image and I send it to the discriminator. I remember there is no way of training G independently. So D exists just to train G. So what kind of label do I want to provide now when I'm training G and I send this image to the discriminator? Any ideas? Anyone? What label should I use now to train G?
Good if the cup doesn't know that it's fake, and bad if the cup can see that it's fake.
Yeah, but I'm training now. Okay.
A real example.
Yeah. So exactly. So the generator wants to fool the discriminator, and since he does, we're going to train it with a label saying 1. And remember, we're only training the generator now. We're not training the discriminator. Okay, this is why I do it with this label of 1. This is the minimum that you see here. And to see it technically, maybe it will help to understand it better. When I do the backpropagation, this is super important that the weights of the discriminator are locked. I'm not going to update them because I'm now only training G. You should note the fact that if I want to calculate the gradient with respect to the weights of G, I have no other choice but doing backpropagation through the discriminator. But I only use it to calculate the gradients. Under any circumstances, I don't update the weights of the discriminator. So the gradient flows, but the update is only here. So you can think about it as the discriminator is just this big loss for the generator. It's just like a frozen loss function, like you have, I don't know, MSE, course entropy, whatever, like this complicated function, which constitutes the loss, and I don't update anything inside this function. And then I only update the generator according to trying to be the best G, so that G of Z best fools D. Okay? And you can see that there is no existence of G for real examples, right? Because when you use real examples, you don't do anything with the generator, and the generator cannot affect it. So only for fake example, only for the fake example side of this term, we have this G over here. So the discriminator tries its best to distinguish between real and fake examples, and the generator tries its best to fool the discriminator to make it believe that the generated examples are actually real. And the nice thing is that the better the discriminator is, the generator is able to get gradients, good gradients that teach it how to create better examples, more realistic examples to fool the discriminator. Okay, so this is like arming race, you know, like they're both trying to get better as possible. And my next question would be, who do you train first? What do you say? Do you train first the generator, or do you train the discriminator first? What makes more sense?
In
Any
parallel?
idea? Yeah, in parallel, that's correct. So I'm going to do this GD thing, and there are many techniques. Some people do 8 times G, 8 times D, and I've heard many things. Okay, but generally I do this in parallel, and we'll discuss why just in a minute. But let's address 2 questions that are usually asked about GANs. So the first one, okay, we were telling this whole story, and why would this work? And this is in light of this bad suggestion I had before, that I suggested before, about just taking random image and random vector. So why would this work? So one thing we need to notice is that D learns a probability. So what D actually learns is to assign this scalar number to each example, which is the probability, saying to what extent, what is the probability of it being a realistic example. And then G trains to sample instances to have the highest probability according to D. So if D can get better at its job, G can get better at its job. And as opposed to the bad suggestion that I was showing you before, in this case, we're not arranging the latent space by ourselves. Okay, we're not saying this noise belongs to this image and that noise belongs to the other image. What we're saying something that is much more simple. We say, okay, here's this noise. You need to create some image that has high probability. I don't care which image, and I'm not saying it's supposed to be this specific image out of the data set. So we don't have this story we were telling about this noise, 2 noises that are very close to each other produce images that are very far away from each other, stuff like this. We don't get to determine this. Okay, we're only saying you do whatever you want, just that it will have high probability. And if you go to the paper from 2014, you will see that you can actually prove that under ideal conditions, and if you get the exact objective and you don't have any optimization problem, which are very bad assumptions, but under these bad assumptions, GAN actually minimizes the JS divergence. This is like a commutative version of the KL divergence, of the Kullback-Leibler divergence. This is called the Jensen-Shannon divergence. The second question, which is very frequent about this, is why do you have to do this alternating? So usually when people first hear about GANs, so they're saying stuff, okay, but why don't we just a little bit pre-train the discriminator, you start a little bit, you do this to the generator, but any of these things cannot work. And a basic thing we need to understand is that the gradients are meaningless when the game is unbalanced. So if you're competing, if I'm going to play one-on-one with Michael Jordan, then I'm not going to learn, and he's doing his best, right? He's not like teaching me. I'm not going to learn to play basketball any better. The gradients are going to be meaningless. It's just going to shoot over my head all the time, and I'm going to learn nothing. This is just a philosophical saying. But let's get practical. So, okay, you want to pre-train the, right, okay. What you're going to use for negative examples? What can you do? You have positive examples from the data set, but you don't have fake examples. And we said before, if what you want to use noise, fine. Then so what you're going to get is that everything that is not noise can potentially be considered as realistic. Okay, you want to have noisy images, you can't do this either because you'll just learn how to discriminate noisy images. Okay, yeah.
What about like strong augmentations on images as negative examples? Will that help? Some distortions, jitter.
Yeah, so I don't think so. I don't think so because a negative example should be something that potentially is trying to be a real example. So if I take all the images and I distort them in some way, then what I learn is that I can discriminate bad examples according to whether they're distorted in some way. Okay, I'm looking for this perfectionism. Okay, I want to create the perfect image. Okay, so that an image that is close to perfect is not good enough for me. I want to get the best I can as possible, and I cannot train D without G. On the other hand, I also cannot pre-train G because what loss am I going to use? If I'm not training D at all, I have this meaningless network which constitutes the loss that I'm trying to train with, and now if D is not training at all, I don't have any loss to train G with. I don't know what I can do. Okay, so the idea is that if I do this gradually, so G starts meaningless. So at the beginning, right, the discriminator needs to discriminate between real images to images that are probably look kind of a smudgy noise. But then the discriminator just gets a little bit better. Okay, because it knows to distinguish between those very easy cases. And the generator now can get a little better because the discriminator got a bit better, so the generator cannot create this smudgy noise anymore. It has to do something that has more characteristics of a realistic image. And then the discriminator gets better because it needs to discriminate this, and so on and on. They're both getting parallelly better all the time, and none of them can exist without the other. Okay, the generator, and to get better, the generator must have the discriminator, and the discriminator must have the generator, and it's this equilibrium between them that is going to get us to be able to learn the distribution and to be able to generate good examples. And so here are some results from 2014, and so these are the results shown in the Goodfellow paper, and I'll explain how this thing is built. So you see these yellow bounding boxes in this right column of every grid. These are 3 examples, which are the nearest neighbor examples from the data set of the almost rightmost column. Okay, to show this is meant to show that there is novelty that is not the same as a nearest neighbor or something like that, and you can see that it is able to generate MNIST digits very well. I think. I mean, these examples look good, and it's able to generate these small grayscale face images that look sort of realistic. I mean, you can tell they're not true images, but they look okay. And at the bottom, you have CIFAR 10 and CIFAR 100. And I don't know what to say about them, because in general, I think these are crappy data sets, and I can never, even in the ground truth images of CIFAR, I can never understand what I'm actually looking at. I mean, I don't know what is this? I don't know. Okay, but generally, it was having trouble doing like natural images. Bigger images were impossible. So a very important development arrived later on in 2015 by Alec Radford. This is called DC-GAN, Deep Convolutional GAN, and he used convolutional neural network with this efficient architecture that was kind of everything was developed from this later on. So you have this vector of noise with 100 dimensions, and then you do this reshaping, and then you have convolutional layers with transposed convolution to enlarge it, and then you get the image. And the discriminator is like a CNN, binary classifier CNN that you would expect it to be with the max pools and everything. And this was able to do these RGB images. So you can see these RGB faces. Some are good, some are scary. Okay, but this was an investment with respect to 2014. And they were able to demonstrate some really nice features. So this is called latent space interpolation. So you see this morphing, and the way it works is that you just go along and travel the latent space. So you do very small jumps for Z, and you change the directions, and you can see this morphing from a face to a face. And it's not perfect, because GANs are not perfect, but there is a reason why this thing would work, at least in theory. And this is just based on these 2 principles, saying that if you train your GAN correctly, if everything is good with this, then every point is mapped to a valid example. So whatever Z you have, you're expecting to get a good face in this example. And the second thing you should notice that actually affects a lot of the things that we do, and we sometimes don't think about it, is that neural networks are continuous functions, almost all of them. Okay, only very rare variants that you can bump into are not continuous. So being such a continuous function means that if you do like a small step in Z, you expect to get small. I mean, it's not just continue. Okay, so it has to be like a Lipschitz or something. Okay, but in general, if you do a small step in the latent space, you expect to get small step in the final result in the image. So if you're supposed to get an image that is A, realistic, and B, close to the image that you had before, so you're getting this nice continuous morphing. Okay, and we're going to have a break in a minute. I just want to cover one last thing in this basic GAN setup, and this is the evaluation metrics. So I'll talk about 2 basic evaluation methods. The first one is called Inception Score, and it's called Inception because Inception is the name of a very good neural network by Google. It's called Inception Network, or it started called GoogleNet, and there is now Inception. I don't know what there is now, but what's usually used for this is Inception version 3. Okay, and it's just a classifier, and the way it works is that if I created a good image, if I was able to generate a good image, then what I expect to get in a relevant classifier that trained for relevant images for this type of data that I have. So what I expect to get is that the correct class will be as high as possible. Okay, so I'll be able to recognize it the best, and I want to have as much confidence as possible, which means very low entropy. If you look at the distribution of the softmax values that you get. Okay, the best thing I can get is 1 for dog and 0 for all the rest. Okay, and a very bad thing is if I have this very balanced thing, very high entropy, which means that the network is not sure what it is that it's seeing. But on the other hand, this is not good because one thing that can happen is, what if I always generate the exact same image? Not just even that I only generate dogs. What if I always generate the same dog? Then what I'm going to get is, for everyone, I'm going to get maybe very high confidence, which is what we said that we want. But naturally, this is not what we want, because when we're training GANs, we want to be able to have diversity. We want to have results that are different from one another. So generally, what I want is that I have a set of generated images, and I average all of them or sum all of them. Then I'm expecting to get something that is way more balanced, okay, that matches the distribution of how each of the appearance of these classes in the data set. So I want to see something that is balanced. So the Inception Score is built just upon this understanding, saying that, okay, so P of Y, Y is like the possible classes. So the general P of Y over the set of generated images, I want it to be something that is more or less balanced. I want it to match the distribution of classes in the data set. But separately, for each example, for each X that I have generated, I want the P of Y given X to have the lowest entropy as possible. So I want these two distributions, like the general distribution of labels and the general of and the distribution of softmax number that I have for a single generated example. I want these to be far away from each other as much as possible, and this is why I want to maximize the Kullback-Leibler divergence between these two probability distributions. Okay. And we usually take the exponent, and this is the range of numbers that we are looking at. Okay, so this is called the Inception Score, and it's based upon this Google Inception network. And this is usually used for GANs that generate images from diverse classes. So it will usually be not very useful if you have this GAN that just generates faces, because it's not clear what the classifier is going to be if you're doing only chairs. So you need the classifier to be relevant to the type of data that you are now creating, like the same distribution.
Assaf?
Yep.
Just a quick question. In terms of diversity, it encourages diversity across the classes, but it doesn't stop you from like generating a single dog and a single cat.
Yes, you're correct. I mean, it wouldn't do that, right? So in theory, you can converge to have like we'll mention later on what mode collapse is, but you can converge to a situation where you only have one or very narrow distribution of examples for each class. Yeah, it can happen. Okay, and the second metric that we have is called FID, Frechet Inception Distance, and I'll just explain the steps you do, and then we'll see what's the reason for it. So first, you take the data set of real images and you take a large set of images. And then you put it again in this inception network. But you don't have to go all the way this time. What you're going to take is this vector, this code mapping that you have in the almost last layer. And you're going to take these IDs of all the images that you used, and then you're going to fit a multivariant Gaussian distribution to it. Okay, you only need the covariance matrix and the expectation value. You calculate them, and you have this Gaussian. Now, this is step 3. Step 4, you're going to do the same thing, but now you're going to do this to generated examples. So you generate many examples. You take this code from right here, and then you create this second Gaussian distribution, multivariate Gaussian distribution, and now you have the Gaussian distribution of the reals, we call it X, and the Gaussian distribution of the generated, we call it G. But this is not Gaussian distribution of pixels. This is Gaussian distribution of semantic mapping of these of both of these images. And the next thing you're going to do is to calculate this thing called Frechet distance. So Frechet distance intuitively is this. So usually when people intuitively explain it, is that when you walk with your dog, you have a leash, and you both walk on these separate paths and different speeds, and you're asking yourself, what is the longest distance that the dog can be away from me? So what is the length of the leash should be? This is just a general intuition. You can read about Frechet distance, but there is a closed form calculation when you want to calculate such distance between distributions that are both Gaussians. So this is just this closed, very simple closed form. This TR here means trace, okay? And these are the covariance matrices, and these are the expectation values. And the idea here of FID is that you actually have a parametric distribution, a Gaussian, and you just take the distance between two such Gaussians, which makes a lot of sense, and it saves you from all these things, thinking about different classes, different whatever, okay, because you have this sort of semantic mapping of vectors, which they show in their paper that it is reasonable. It is reasonable to do this for. I mean, a Gaussian distribution for such a semantic mapping actually makes sense. One thing you should pay attention to is that FID depends on the number of samples. You're going to get a different result if you generate 100 examples here, or if you generate 10,000 examples here. So it's generally very important to generate a lot of examples, and indeed it takes time to calculate FID. You need to run a lot of data through the network. And it can take time, depend on how big your data is. Okay, but you should pay attention to this. Okay, we're going to have a break now. Let's have it a 8 minutes break until 20 past 10. Okay, makes sense, and then we go on. Okay, we're back. Please turn on your cameras if possible. And okay, so we had this introduction, and now we generally understand GANs better. And the next thing we're going to discuss is this thing called image-to-image translation. So we're going to diverge from the basic setup of GANs to something a bit more special. And say that now we want to do this action of translating an image from some domain to another domain. So in regular GANs, we're doing this noise to image, okay? But say now that I want to go from distribution that is not this noise, but for example, I want to do this sketch to a shoe, or map to a satellite image, or a picture at day to a picture at night, or low resolution to high resolution. Okay, so this is what we're going to discuss now. And we need to understand this element called conditional GAN as opposed to the regular GAN we discussed before. And the main difference is that in conditional GAN, you don't have the noise. I mean, you can have also noise, but the basic setup, instead of noise, you have this X coming. You now have these pairs of images. You have X and Y. You get them paired. Okay, for example, sketches and images. These are examples, just like in supervised learning. Okay, and you have X and Y. And now instead of Z, you input X to the generator, and you expect the generator to transform X to be a Y. Okay, and you have the real Y's, but a key difference is that the discriminator expects whether it gets a real Y or a fake Y. So it also expects to always get an X. So the discriminator wants to receive pairs of images as its input. So it needs to decide whether Y is real according not only to whether it looks realistic, but also whether it matches X. Okay, so this is a conditional probability, P of Y given X. This is what the discriminator, the number, the value that the discriminator eventually returns. Okay, so mathematically it looks very similar to the GAN that we already know. There are only two differences. So one difference is that instead of Z, you have here X. And the second difference is that whenever you apply the discriminator, you have this Y, but also X. Or instead of Y, you have G of X, which is the fake Y, and X. So you have to decide about Y in light of what you see as X. Okay, is this principle understood? Okay. Is this okay right now? Great. So this is a conditional GAN, and in this work by Philip Isola from 2016. It has this long name, but everyone calls it Pix to Pix. And you want to do this thing. You want to turn a sketch to an image or all the other things that you've seen. So you'll have the discriminator, and you're going to train it to take pairs from your data set, two images that are paired, and you're going to show it to the discriminator, and you say, okay, this is a real example, just like before, just that you have this pair, not just a single image, and you say, okay, this pair is realistic. On the other hand, in the generator, you have this sketch. The generator trains to transform this sketch to an image, but the sketch also goes to the discriminator, and now it depends whether you're training the discriminator or the generator. If you train the generator, then you want to give this a label of real and only update weights of G. If you're now training the discriminator for a fake example, you want to only train these weights of D and say that this is a fake example. Okay, is this clear? It's very similar to the regular GAN. You just have this condition added, right? Are we okay with this?
Why use a GAN for that?
Oh, that's a great question. So remember this question, we're going to get to it in 2 slides, okay? But I really, this is a very good question. Okay, and again, we have this loss over here, but in Pix to Pix, they did another thing, which actually has a lot to do with the David's question. So they're also using, since this whole setup is a supervised learning setup. Okay, you have these pairs. Then this is what I believe the reason. I'm sorry, David or David?
Either.
Okay, so this is I think the motivation for David's question, that you can also do this. So they're saying, okay, we know the exact mapping. We know which X belongs to which Y. So we're now going to take this just L1 loss between X and Y, and we're going to add it 2. And so we're going to have these 2 losses. So one is this generative loss, and one is this, you can call it the discriminative loss that they're using. And in a talk, I once asked why you need this L1 loss 2, and the answer was to stay in the neighborhood. And this is what I interpret as it's easier. I mean, if you could potentially do only the first loss perfectly, then it will be good. But optimization is hard, and this L1 thing is makes it more stable. We'll talk about such things later on. Okay, so your final objective is both of them with the weight to the L1 loss, and they were able to do this really nice thing. So you can see this stuff that some we've seen before, but you can do this segmentation map to this realistic. And a thing in common for a lot of these examples is that in a lot of the cases, one side is very easy to do. So going from this realistic image to a segmentation map, you've seen this before, right? Doing segmentation, you have networks trained for it. So this is relatively easy. And so you can create many example pairs and then train the conditional GAN to do the opposite thing. But one example that I want to pay attention to in particular is one that looks the simplest one, and this is the colorization thing. And here we're going again to the question that David just asked. So why do I need a GAN? I have X, I have Y. I can just have this regular, normal supervised learning scheme and train it. Any ideas?
You have multiple good answers.
Okay. I'll go with it. I'll lead to it even more by the provocative question, which is: are all butterflies yellow? Okay, I think you know the answer to whether it's true or not. We know that a butterfly can be yellow and green or red or whatever, and many things have multiple possible answers. And what would you expect to get if you train a supervised learning scheme over this colorization task? What do you think you'll get? I'll just use MSE. Sorry, Dana?
Average of something?
Average of something is correct. So I'll probably get the average color for everything that I can get. So probably a butterfly will always be just gray. Okay. And this is a very important observation for understanding generative models in general. So it's not just this cool thing that I can generate new examples. Even this task that sort of looks like a supervised thing, which it is supervised. We have the labels, it's supervision. But the problem is when you don't use a generative model, is that you only have one choice. And if you have a distribution of possible answers, then what you're going to get from a discriminative model is a centroid. At some cases, this centroid can be good. But at many cases, and this is the cases where we choose to use generative models, this can be an unlikely centroid. For example, I think there are, I know there are gray butterflies, but it can, you know, if there are, let's say I have this recognition of like checkmate figures, chess figures. So they're either black or white, and I'm trying to create them. So probably what I'm going to get is I will always color them gray because this is the average, and there aren't actually real gray chess figures, right? And the generative models say I'm going towards a high probability. So this is the type of results that I'm going to get from generative model. There are some cases where you can argue which is better. So image denoising, I have image and it has noise. So usually we use discriminative model, but maybe the future is, and people do it, I'm not saying they don't, people do it for a long time, for things like this, for super resolution, for other stuff, saying, wait, for what we call inverse problems, there are multiple possible solutions, and we're always going to their average, and this is why we can't get any better in this. So maybe we should think about many things that we used to do with discriminative models. We should actually try to do them with generative models. Okay, so this is like an important observation. General thing about generative models is not just this cool stuff of creating GANs, it's a total approach. Okay, but now in this image-to-image translation thing, we want to say, okay, what if I don't have these pairs? Okay, so in real life, we're able to, as humans to do these analogies, and we don't have this set of pairs, and there are many types of data that we can't have these pairs too. For example, these famous horses and zebras. You don't have real images of a horse and a zebra just in the exact same position, pixel by pixel, right? You don't have such a thing. So instead of a list of pairs, what if we only have a pair of lists? Okay, it's a much harder problem. There is no supervision here, no explicit direct supervision. You just have two data sets. And this is when they came up with this really great thing called SyleGAN. Okay, and SyleGAN works like this. Okay, so let's say I have this input image of a horse. So I'm going to have more than one generator. So the first generator, I'm going to call it A to B. So A is the horses and B is the zebras. Okay, so I'm going to feed this to the A to B generator. Oops, sorry. And I'm going to generate, hopefully, maybe something that looks like a zebra. To make sure I do, I'm going to feed it to a zebra discriminator. So what we have up until now is just a regular GAN, right? Or almost. The input is a horse. It's different, but you get a horse, you generate a zebra, and you have this discriminator here. Okay, but here's the special thing that I'm going to do, because this can make sure that I actually get a zebra, but this doesn't make sure that this zebra matches exactly the horse that I have here. So to make sure it does, I'm going to take this generated zebra and I'm going to feed it again to another generator called generator B to A. Okay, and this is a generator that goes from zebras to horses. And now I'm going to generate what I hope is not just a horse, but the horse that I already had. And to make sure I do, this time I'm going to use a simple L1 loss. Means that I want to reconstruct the original horse exactly back again. So this is a cycle thing. You see, I went from one dimension X, went to Y. I made sure that it belongs to the distribution of Y. So this is what makes sure that I do go to Y. And then I went back to X and made sure that I'm going to, as close as possible to the X I came from. Now, I have to also do the other side, because right now, this generator only trained in this supervised scheme, right? In discriminative scheme. So to make it work, I need to do also the other side. Okay, and the other side, now we start here down. Okay, so the other side, I start from a zebra. And I can take the zebra to the zebra discriminator saying, okay, look, this is a real zebra, okay? But now I'm going to do the same thing I've done from horses to zebras, now from zebras to horses and zebras back. So the zebra goes to the generator, I generate what I hope is a horse, the discriminator will help me make sure that it is a horse, but I want to be the horse that matches this zebra. So the horse is now going to go to the A to B generator again, and I'm going to create a zebra and use this very simple L1 loss to make sure that I'm back again to the same zebra. So this is called a cycle consistency, and this is the SyleGAN. I have to say a little bit of sad truth about SyleGAN is that since you're using convolutional networks, the most natural solution will actually be matching not too bad pixel to pixel, the zebras to the horses. The cycle thing is very elegant, but it only helps a little bit. So this is the sad truth about this. I mean, it's nice, it gets it a little bit better, but most of the pixel to pixel matching actually happens naturally. This is a prior when you're using convolutional neural networks. So there I said this, and here are some results. So you can see, you can take a picture by Monet or a realistic photo. Here are the horses and zebras. You have this really cool winter to summer, and you have this artistic thing of taking photographs and transforming it to a lot of painters, Monet, Van Gogh, Cézanne. I never know how to pronounce this Japanese painter's name. And some people online were also using SyleGAN to do some stuff, and I just chose one of them that I found a little bit funny, which is taking celebrities to ramen bowls. So this is how it looks like. So you get celebrity to a ramen bowl and back to a celebrity. it's not very impressive, I think, but it is funny. I like this one the most. Okay. And they were also joking about some world leaders riding horses. And that's it about image-to-image translation. And the next topic we need to discuss is how hard it is to deal with GANs and what can we do. And we're going to say a few things about this now, but then later on through all these topics, we're going to collect this list of possible tips, and we'll have this list at the end with all of them. Some are trickier than others, but these are things that can help you deal with GANs. And so one thing we should all be aware of is that training GANs is hard. So we were saying the great things that we're able to do using GANs, we were just naming them. But what I didn't say up until now is how really hard it is. They're usually very heavy networks and they suffer from really big problems. So the first problem, as I see it, is the stability problem. So you have the generator and you have the discriminator, and we already said that if you have imbalance, if one is stronger than the other, then the gradients are going to be meaningless, and then you will not be able to get any training done. So most of the time when you train GANs, what you worry about is balancing. And usually what's going to happen is that the discriminator is going to be too strong. And then you get to the point where the discriminator just immediately says everything that comes from the generator is fake without any problem. And then nothing happens and you're not improving at all. And so you need to do this game trying to balance, the discriminator will be not too strong, but just as strong as the generator. Discriminators tend to be the stronger ones because their task is much easier, because binary classification is much easier and requires less expressiveness and parameters than generating an image. The other thing is very famous. It's called mode collapse. So this is a real experiment shown with the 2D data. So let's say I have this distribution. You see this ring of Gaussians, and I train a simple GAN to match them. So what you're going to get, these are the steps you see, and finally what you get is this one that actually matches not too bad to this small Gaussian over here. But what about all the others? And you should be aware that the discriminator is happy if this is the result that you have. So the discriminator has nothing bad to say about this, because whenever you generate an example from here, the discriminator likes it. It says, okay, this is with high probability. So this is called mode collapse. So in practice, what may happen is that you're not really going to generate the same image all the time, but you're going to get to generate images that are very similar to each other. This is called a mode. You see this, you have one area around the peak. This is one mode. So usually you're also not going to just have one mode. You have several of them or tens of them, but you're not going, almost always, you're not going to be able to cover all the distribution. Okay, so GANs don't really succeed at the task of learning the distribution. They're just find this possible set of modes that make sense, and we try to make this set as large as possible. But you can see also theoretic work saying that as opposed to everything we said before, GANs are not really able to learn the distribution of the data, and this is called mode collapse. Another very annoying thing is that GANs can actually overtrain. So everything can be going well, you can have a reasonable result, and then you wait some more, and then you get this crash or something, or instability, and the discriminator crushes the generator and everything just falls apart. And you're not used to it. This doesn't happen usually when you train a classifier. It usually wouldn't just get worse just all of a sudden. What's happening? Okay. And the fourth thing that I want to say is how frustrating it is that the losses don't reflect what you really want them to reflect. So you can have the discriminator loss for the real and the discriminator loss for the fake and the generator loss, whatever you want, you can show them. But since they're competing each other, so it's not like you have this loss curve that is going to get lower as long as you go. So the only thing you can see here is whether they're balanced, but they can be balanced and all very bad. I mean, you get the same result when you have a very bad counterfeiter and a very bad cup. Okay, it's about the same thing as if you have a very good counterfeiter and a very good cup, which is what you actually want to achieve, right? So there is no, other than stability, following these losses cannot tell you how well you're doing, what is the quality of what you are now producing. You can do some evaluations, but we are really used to this monitoring the loss thing. And then when you go over to GANs, it's very hard to monitor and to understand, to analyze what you need to improve, okay? So we're going to see some tips and tricks. I'm going to quickly mention some very basic ones. And these are from, there is a paper that those interested, I recommend you looking at. It's called Improved Techniques for Training GANs. It's from 2015. And it was when there was like a year of experience of dealing with GANs. So Ian Goodfellow together with SyleGAN, they wrote this paper, and they have this just a list of methods. Some of them are outdated. I want to mention one of them. It's called batch discrimination. And I'm not going to get to all the details, but it actually makes a lot of sense. And the thing here is to deal with mode collapse. And one thing you can do to deal with mode collapse is that in the discriminator, we always work in batches. So the discriminator gets a batch of either real or generated image, and we trick the discriminator in such a way that it doesn't judge instances separately, it judges an entire batch. So when it gets a batch from real examples, they are diverse, they're different from each other. And if in the extreme case, I generate a batch and all the images are just the same, so the discriminator at some point will be able to say that this is fake because it's not used to see such repetition. Okay, and small things that you should do is to use this leaky ReLU activation, usually in D, sometimes also in G, because the instability can get, one spike can bring you to this situation called dead ReLUs. You can read about it, and I'm not sure if we mentioned it before. And an activation called leaky ReLU is able to deal with this. Also, for the stability thing, we almost always like to use batch normalization in GANs, or this thing called instance normalization, which is like batch norm, but not over the entire batch, but for each instance separately. And I'm not going to explain exactly what a spectral norm is. It's not a layer; it's an action that you do between the iterations. Okay, and it's actually, so it's doing spectral normalization to the weight matrices. So you divide them by their highest singular value after each time. But why is this justified in terms of backpropagation? So there is like a 20 pages paper about it, and you're welcome to read it. And the last thing is that people started suggesting many types of other losses. So one very famous is called the Wasserstein GAN. And in the Wasserstein GAN, you define just a different objective. So we had this regular GAN over here. You see this for the discriminator, this is what it maximizes. And for Wasserstein GAN, you see it's sort of similar, but it's without the log thing. So you want D of X to be as high as possible without the log, and D of G to be as low as possible because you maximize the minus of it. And it turns out, you can say many things about them. I'm not going to say too much. I'm going to say that it turns out they were able to prove in the paper, just like that the regular GAN minimizes the KL divergence. So this minimizes this thing called Earth mover distance. Okay, so I guess some of you know, it's like if you have these two piles and you need to do the minimum job to move sand so that you get a pile that looks like this. And so you measure this distance, and this Wasserstein GAN in these ideal conditions that are never actually met minimizes this sort of distance. And in a lot of GAN tutorials, people go through other possible objectives. I'm just going to show you a lot of them. That a lot of them exist. So you have the Wasserstein GAN, and you have the Wasserstein GAN with this GP thing is gradient penalty. In particular, I like working with this LSGAN, least squares GAN, that you see. It's very similar, but it has this squared loss, just distance from 1 and from 0, and there are many others. Okay, and I'm not going to go through all of them, just because there were these people from Google, and they were kind of skeptical, and we're talking about several years of many works showing different various GAN objectives, and each one explaining a lot of hand waving theory, why it works better using this. And each time such a paper came out, they actually got state-of-the-art result in terms of FID, okay, Frechet Inception Distance. So these guys at Google, they had a lot of computing resources, and they decided to check it, and in particular check how hyperparameter tuning affects it. So you have many things like the architecture and the learning rates and the type of gradient descent method that you're using. So they mapped 100 hyperparameters, and they actually did this grid search and used a lot of compute, and on 3 different data sets they played on really a lot of setups to test this. And I'm going to explain what you're seeing in these plots now over here. So we have 3 data sets. This is why we have 3 plots: the Fresh and MNIST, C410, and the SyleGAN. And they took each one of these type of GANs and they played with it with 100 hyperparameters. And for each one, they mapped it. So the y-axis is the FID. So lower is better. Okay. And they took the mean. So this is the, for example, this line you see here, or the lines here, this is the mean performance. And I think the colored is 1 sigma and the uncolored is 2 sigma of distribution of FID results. And they were checking what affects better. And the really sad conclusion that rises up when you look at this plot, you see all these methods, you see that clearly there isn't one method that dominates another. So for example, let's look at this Fresh and MNIST here. You see, if you take the best performance by that they could reach after thousands of experiments, you can see that more or less all the GANs, the basic one and the LSGAN and the Wasserstein GAN, the best results of all of them is very, very close, almost the same. Okay, and they all spread along a very big distribution of possible results, including very bad results like over 100 FID and stuff like this. And this actually shows that no technique is actually done. You can't say that Wasserstein GAN is better. You cannot say that least squares GAN is better. All of them can be better, and some can have like good effect, but it turns out that you can't say it dominates, because tuning the hyperparameters actually does a lot more than choosing the type of GAN objective that you're going to use. In particular, I like the black star that you can see in every such column. The black star is they put it at the spot where the original paper of this work, say the LSGAN, the Wasserstein GAN, so the original paper, the results that they reported, that they had, that they were able to get. And this is nice because it shows how hard the students worked on this hyperparameter tuning. So for example, for the Wasserstein GAN, you can see that what they were published was pretty high in the 1 sigma, I think because it's the oldest one. So they didn't have too much competition, so they didn't have to work too hard. But something like the LSGAN guys, they worked really hard. So they get the black star very low, almost the lowest possible result. They probably use this automation of hyperparameter tuning. But this whole thing is also teaches us something general, and I'll take this opportunity to things that may sound a bit like preaching, and is that if you do a new thing and it works well because you worked very hard on tuning from all the sides to make it a better result, it doesn't scientifically means that it is better. Okay, and this can be quite disappointing, and unfortunately this is very common in our field. So this guy Mark Sarufim actually did this diagram that shows how usually this thing works. So you start by find something that is state of the art on archive, then you find its code, then you do these changes and you try and do it a lot until you get better result, and then you publish. And if I may add, what you usually do after this is do this hand wavy theory saying why the results you got are better, and you're saying like very deep stuff about game theory and I don't know what, and you're saying of course this has to be better, but the truth is that you're just more persistent on the hyperparameter tuning thing. Okay, so this is a general thing that I hope the message was clear about. Let's talk about some nice tricks that can help us. So this is called mode seeking GAN. Okay, and this is used against mode collapse, and I personally used it several times, so it really works well. I kind of like it, and this has a very simple principle. So let's say I have this GAN. It can be conditional or not conditional. They showed it for conditional GAN. Okay, but I also have these noises here. Okay, so instead of just having a noise to the generator and to the discriminator regularly, so what I'm going to do, I'm going to have these pairs of noises, and when I get this pair of noises, it's going to be mapped to a pair of generated results. So I get two results, and for each such pair of results, I'll just say that I want them to be as far as possible from each other, but with respect to how far the noises were from each other. So I'm maximizing the distance between the generated images in some metric. I think they use L1 metric. So, so the distance between the images divided by the distance between the noises, I want to maximize it. So this means that if the noises are very close to each other, so the images can also be relatively close to each other. But if the noises are very far away from each other, then the images have to be very far away from each other too. This is super simple. This is just doing what you know, expressing what you wanted to achieve, and it actually worked very well for me the several times I used it. So I want to mention this trick over here. Another very important thing that helped a lot, especially in conditional GANs, is called multi-scale discriminator. So this is very simple and it's inspired by classical computer vision, and it says, okay, we have the generator and discriminator, but let's judge the image at multi-scale. So instead of just judging the image in its original resolution, I'm going to now downscale it and judge it with another discriminator that is trained especially for smaller sizes, and another one, and I have this pyramid of discriminators judging all the scales of the image. And this is very helpful in the sense that you can judge a global structure and not just tiny images. And this is inspired from the classical computer vision, and this is one of the main improvements in this work called Pix-to-Pix HD. I'll show you this and some other tricks they use were big improvements. So this is the original Pix-to-Pix. When you have the segmentation map, this is the image you produce. So it's impressive to do this in 2016, but then in 2018 you can see how impressive it looks. You see the flickers, right? Okay, so using all these tricks made this conditional GAN a lot more impressive and much better. Okay, the next thing we'll mention is this set of GANs called progressive GANs, and this is also related to this multi-scale thinking, but here we have both the generator and the discriminator as this multi-scale thing. So you start with a very simple set of generator and discriminator that do very low resolution images. And then as you go on, you add layers and you make the resolution bigger. And so you need to add layers to both the generator and the discriminator. And you go on and on and on until after the training progresses, you're able to generate very nice resolution images. So you can see in this animation how it works. You can see the training days here and the resolution here, how it grows. So at the coarser scales, it takes not that many times. You see, until the 512 resolution, it took 7 days, but now it's going to take 1 more week to train over to the final resolution of this work, which is 1024. So it's 2 weeks training, coarse to fine. And this was the first time where we could get very realistic images. And this was called progressive GAN. And a very important advancement in this from 2019 from NVIDIA is called the SyleGAN. And the SyleGAN has many other tricks, but it is built upon this progressive GAN and uses this style module. And they're using this thing called ADA-IN. So this is adaptive instance normalization. And the idea is that you want to inject noise into deeper layers of your generator. But the way you're doing it is not just as concatenation or input, but the noise determines how you normalize in normalization layers, how you normalize the values that you have flowing through the network. Okay, so so you get the noise is mapped, and you get this scale, and bias, and then you do normalization. This is like batch norm, but you normalize every instance separately. You don't want to normalize 2 instances together, so it's called instance normalization. And that adaptive means that this transformation, the new bias and variance are determined according to the noise. And they were able to show these really super amazing results. So this is what it looks like. This is super realistic, and you can control the style. You've seen like in previous classes that style is the second order statistics of the deep features of image patches. So the deeper you go, you control smaller details, and when you do the coarse things, that you can change general structure, the gender, and stuff like this. And the results are super realistic, and this made possible this website called thispersondoesnotexist.com, and you can go, and every time you refresh, you get this a new face which looks super realistic, but it is actually generated. I don't have time to show you, but you can also visit which face is real and compete each other if you're able to distinguish real from fakes. And I also recommend going this website called This X Does Not Exist, because this is a list of other websites of This Cats Does Not Exist, This Rental Apartment Does Not Exist. They have for text, they have for music, and it's really cool. And there was a very important challenge in Kaggle by Facebook with $1 million prize for identifying fake images because of the influence these deep fakes have over the media, and what we're able to generate and do fake news and whatever. And people are very worried about forensics and other stuff, and the world is changing rapidly. So video forensics are not going to be as reliable as they used to be. Okay, so we don't have a lot more going on, but I am going to need about 10 more minutes of your time over this when we're supposed to finish in a minute. So I hope all of you can stay, because I really want to show you everything. So the next thing is scaling up GANs. So we're talking about in particular 2 steps that we're taking. One is called self-attention GAN, and the other is Big-GAN. And the purpose here is to be able to generate diverse images, not just of faces, not just of chairs, not just of outdoor views, but to take and generate ImageNet. Take over all these 1,000 classes, we want to generate diverse images. This is a much harder problem, and they had to use a lot of tricks which can be very useful to understand. And this gradually built this network, these GANs that were very powerful. So the first thing is called class conditional batch normalization. And this is sort of similar, a little bit similar to the ADA-IN that we've seen before. And the way it works is that you have embedding for every class, like this one hot vector. This goes through this learned layer that maps it to a vector, to two vectors actually, which are the variances and the means of the batch normalization layer that you're going to have. And this happens for all the batch normalization layers along the network. So this is how you're able to generate images from various classes. So for each image, you have also its label of the class, and now you can control from what class you want to do by normalizing all the data along the network. Is going to be normalized to this embedding according to its class. This is a very nice way of having a single GAN, but use the normalization like having 1,000 different generators. You're all familiar with self-attention from the previous classes, and using self-attention in GANs, in such GANs was extremely helpful because you have this connection between different places inside a single image. So if you generate a face, for example, you don't want one eye to be blue and one eye to be brown, and using the self-attention gives this awareness of resembling of different elements inside this single image. We do this trick of splitting the noise to parts and then injecting it to different parts along the network, and this helps us avoid mode collapse and get more diversity. And I need to say that the most important thing that made Big-GAN good at its job is just the compute. We need to be aware of this. So we have a list of tricks that were used according comparing to the self-attention GAN baseline. And if you check this table from the paper, you see that the biggest advancement happened because they had a huge batch size and more channels in their layers. These were the most important things. So still compute is the most important. And we mentioned the spectral norm. This was very helpful. So spectral norm made training Big-GANs possible. Without them, it's very imbalanced and everything doesn't work. And the last trick is called the truncation trick. So the truncation trick is very simple. You say training all goes the same, nothing is changed. But at inference time, when you want to generate new images, you're not using the Gaussian distribution anymore. You generate images without taking this tail. So you define this threshold where you don't want to take, because these are unlikely images and you don't want to use them. So you have to be careful. If you do this too much, you're going to get this mode collapse. And if you're going to take the entire thing and not cut the distribution, not using this truncation, then you also generate things that look very weird and don't make sense. So they were able to do very impressive results from diverse classes, but this is cherry picking. If you check what else they were doing, so you see that many of the results are not as good. And we should say that the reason is that this is a much harder problem. So I want to show you that we just had these two branches of types of GANs. So I have this SyleGAN branch and the Big-GAN branch. So SyleGAN is made to train on one domain. The most famous one to train it over is faces. And the Big-GAN branch uses this class conditional thing, and you train it over ImageNet, which is much harder. You have structured data, so faces are all aligned, the eyes are in the same place, whatever. And here you have very versatile data. Think about how different a dog is from spaghetti bowl. And here you have this progressive growing GAN, and here you have the self-attention. They are at the same row in this table, and the reason is that both of them are this branch's method of being able to deal with a global structure, not just local, to have this global understanding and create images that are globally. And lastly, the SyleGAN branch does really amazing results. It's hard to tell them from real ones. And the Big-GAN branch does some amazing results. Not all of them are amazing, but the main reason is that you cannot really compare the challenge. The challenge is much harder for this Big-GAN branch. Okay, so I want to quickly show you some cool stuff before we wrap this up. Sorry if I'm taking your time. And these are some applications that use generative models. And here is a very cool thing that uses the very basic pix-to-pix with some little improvements and is able to do really cool things. So this is the pix-to-pix setup with a few improvements. So instead of this L1 that we had before, we are now using VGG loss that you've already heard about. So we take distances between VGG features. And what we want to do is motion transfer. We want to have, for example, a professional dancer dancing, and I want to be moving like this professional dancer does too. So what I can do is I can do this thing, this pose estimation. There are many networks that do this, and translate this image to this stick guy over here. And then I need to normalize it to have the length of its hands and legs to match my hands and legs if I want to do this for myself. And then I can use this pix-to-pix setup to transform back stick guys to pictures of me, to video of me doing it. Okay, so there's nothing more to it. It's pix-to-pix applied to this very cool idea. So you can see how it looks like. This is a professional dancer, and this is one of the students doing this work. And you can see that you can transfer the motion. It's not perfect, but it's kind of impressive to see that it's possible. We don't have that many times, so I'll skip to show you some more examples. These are the two students doing the job. You can see how they dance very accurate, like this source dancer. And this is the very challenging ballet. And you can see how it makes them dance really impressively. So this is a very nice application. I want to show you mention one cool thing and I think important. It's called GAN dissection by David Bao. And they were just investigating GANs. And what they were doing, they're saying, okay, let's check which units in the network are responsible for which outputs. So one way to do this is to have this segmentation using a segmentation network. And they take the results and they apply segmentation. And then they check which units were activated for which pixel, for example, for the trees, for the houses. And then they were able to have this mapping between units to various elements in the image. And once you're able to do this, you can have this mapping and you can do this painting. Okay, so you change this, and now you have you can see in the animation here you can change these. You can take an image and you can realistically change elements by changing the activations of the units of these matching pixels. I don't have a lot of time there is much more to say about it. We don't have a lot of time, but I really recommend you looking. This is a set of works, and I really recommend you to look at it, or it talks about it by David Bao, which is great. And here's a little bit something that is very relevant to us. And these are GANs that you can train on just a single image. And I'll mention here two works, but the main thing is that you have this either input or noise vector, and you can you input it to a generator, and the result goes out and judged by a discriminator. But the discriminator is a fully convolutional network that doesn't just return a scalar, it actually returns a map. And since it's fully convolutional, each pixel in this map actually means to what extent I believe that its receptive field, this patch from here, is real. So I can simply actually train it on just a single image. So the real examples are going to be from the original image I have, and the fake examples are going to be generated here. And what I'm able to do then is to create a new image which has the same distribution of patches as in the original image that I have. And two works that I'm going to mention. One I was a part of, and it's called InGAN, internal GAN. and the other by Tamar Chacham and by Tom Michaeli and by our Tali Dekel. And these were able to do exactly this in somewhat different techniques, have an image and then create different instances, but with the same patch distribution. So you see, for example, here we have this mountain and water, and here we have this different setup. So we have more peaks in the mountain here, or we have these birds over here. So all of these are pictures of birds, but they have these different locations. And in our InGAN, we were doing this for retargeting. So we wanted to reshape the image, but keep the original elements in their original size. So you can see that we can take this fruit stand and extend it, and you see that fruits aren't stretched or being shrinked. You just add more fruit or more boxes, and you can also do this for various transformations. You can read more about both of these works and see talks about them. There are many of them. And the last thing that I want to show you, so you had this class with Tali about explaining what's going on inside neural networks. So the last thing that I want to show you is this work we've been doing. It was in Google, and I was there, and Tali was also there, and we wanted to use generative models to explain classification networks. So everyone knows that you take a classification network, you take an image, you get the class. But what if I want to do something that is more or less the opposite? I want to check which other images, if I input them into the network, I get the exact same feature map here. Which other images apply to this? And I don't want one image, I want to explore through the subspace of possible images. And I actually want to do this to all the layers, not just one of them, to be able to explore which are the images that match this feature map. And I want to do this in a single feed forward for whatever image I want. So this is what we were after. We want to check to understand a discriminative model using a generative model. And so the basic approach is, okay, we have the classifier, we're not going to touch it, it's locked and it's already trained, but we're going to construct a generator, which is sort of, has this mirror-like architecture with respect to the classifier. And all these elements are now connected. And when I train it, I can activate each such connection. So for this lower thing, for this lower layer here, I can activate it. And then when I jiggle with the noise, this is how I can travel through the space of possible images. And I can go deeper and have more major changes, or even deeper. And we train it with 3 losses. So one is the adversarial loss. So we use a discriminator to make sure that this image is realistic. The other one is called diversity loss. This is the MS GAN that I just talked about before. And the last one is called the feature reconstruction loss. So we want to make sure that this has the same semantic meaning as the original image. So we take it and it goes again through the classifier up until the relevant layer, where we just take the distance between these 2 feature maps and minimize it. So these are the 3 losses that we use. And the cool thing is that we don't have to use the same layer for the entire image. So we can use this mask, okay? And then we multiply this mask for this layer here, and we take the anti-mask for this layer there. And now when we jiggle it, we can only change the background, but leave the bush untouched. And we have many applications, which I'm going to skip a lot of them. You've seen the basic one, and and there is this thing called repainting. So you've seen this bush thing, but here are some more examples. So you can have this hiking thing, and you have the image of yours, and you use this mask, and then you can change the view. So you can upload to Facebook and say that you traveled in many different places. And you can do another cool thing, which is called semantic image decomposition. So say I want to put this church in both of these scenes, but I don't want to put this exact structure. What I want to do is to have something that has the same semantic meaning as a church. But to make it match the scene. So when I do it, I get this really nice thing. So you see, these are entirely different buildings, but both of them can semantically be described as some sort of temple, but they match the scene that they're in. And I'm going to skip because I already took too much of your time. This is called relabeling. And you can see that I can just, since all of these have this class label, so I can play with it and say, okay, this was a highway, I want to be a different class, desert road, or this was a mountain, and now it becomes a volcano. And sorry for taking a lot of your time. I think we're done here. I have this list with a lot of tips and tricks. So most of them we've already talked about. And so I'm going to stay when we're done with this list on if anyone wants to hear about it and ask questions about, because there are some tips that can be valuable for people fighting with GANs, because as I mentioned, it's very hard to train GANs. So that's it. I'm quickly going to mention that we together learned how GANs basically work, and that you can use conditional GANs for do this image to image. And there is this endless set of works of improving GANs and getting better results of GANs, and many tips and tricks that can help you to be able to generate new data. And I guess the most important tip is don't start from scratch. Okay, you don't want to start from scratch. Start from something that someone did, because starting from scratch and getting it to work takes a lot of work. Sometimes you don't have another option, but if you have the option, don't start from scratch. So I want to thank you. Thank you for being here. And one important thing. So this week's tutorial is going to be about LSTMs and RNN. LSTM stands for long short-term memory, by Achiad. He was in reserve duty, so last week he couldn't do the tutorial, so he's going to do this week, which means that the tutorial we wanted to have this week about generative models by Niv is postponed to next week. And next week's lecture is going to be given by Tali, and it's going to be about self-supervision. Okay, now I'm really done, and I'm really sorry for taking too much of your time. And I'm going to stop the recording now. And if anyone has any questions, I'll be staying for a few minutes. So thank you all. Thank you for being with me. Sorry for the time.